Good afternoon, all delegates from Asahi Foundation, speakers, and audience for today. And welcome back to the afternoon session of the 32nd special seminar between Chulalongkorn University and Asahi Foundation. Okay, I believe in the afternoon we have 7 presenters, and each one will have 10 minutes for presenting and 5 minutes for question and answer. Okay, and to remind the speaker, you should observe, I think, 2 people over here that will show a sign that when your time closing to the end, like I think there will be a reminder of 3 minutes and 1 minute before the end of your presentation. Okay, we can start right away. Our first presenter. Okay, our first presenter is Dr. Manasavi Suttipong from Faculty of Science, and her topic will be on the optimization of new electrolyte composition for high-performance lithium-sulfur batteries, a combined molecular dynamics simulation and experiments. So if you're ready, you may present.
Thank you very much. Good afternoon, everyone. I'm Manasavi Suttipong from the Department of Chemical Technology. And my talk today is about optimization of electrolyte composition for high-performance lithium-sulfur and also lithium-ion battery. I combine both simulations and experiment. First of all, I would like to acknowledge the general support from the Asahi Glass Foundation, Fundamental Fund, PMUB, and the Computational Resource from Thai SC. I also want to thank the CU Energy Storage Research Team and some of my graduate students who contribute to this research. And in today's presentation, there are 2 key areas. First, new electrolyte formulations for safer lithium-ion battery, and another one is development of cellulose-based solid-state electrolytes for lithium-sulfur battery. Most lithium-ion battery electrolytes are based on carbonate solutions, and this leads to several challenges such as high flammability, low lithium-ion transference number, electrochemical and thermal instability. These factors make safer electrolyte formulations a critical research area. To improve lithium-ion battery electrolyte, researchers are investigating alternative systems like sulfur-containing solvent. For example, here mixed sulfurane in the carbonate-based solvent, and also fluorinated solvent like fluorinated FD37. It is a mixture between fluoroethylene carbonate with dimethyl carbonate. Unfortunately, further research is needed to clarify how these co-solvents interact with other compositions and influence the battery performance. So, the objective of this work is to develop safer electrolyte formulations by studying co-solvent effects on the solvation structure and dynamics property using molecular dynamics simulations. There are 2 key investigations. First is co-solvent contents and another is co-solvent types. We make a simulation box. The lithium salt is lithium PF6, the common salt mixed with carbonate-based solvent. And we use non-flammable co-solvents. There are 4 types of co-solvent that are going to be mixed in the system. First is tetamethylene sulfone or sulfolane or TMS here, dimethyl sulfoxide or DMSO, fluoroethylene carbonates or FEC, and succinylnitride or SN. We examine how co-solvent impact diffusivity of lithium ion and P-F6 anions. And in general, high diffusivity is linked to improved ionic conductivity, which is important for fast charging and high energy density. And what we observe here, DMSO increased diffusivity with rising co-solvent content, unlike TMS or FEC or SN. We use Nernst-Einstein equation calculate ionic conductivity, and we find that while TMS, FEC, and SN show reduced ionic conductivity as co-solvent content increase, DMSO exhibit enhanced ionic conductivity. This support better ion movement. Here I show the transference number. The lithium ion transference number indicate the proportion of electric currents carried by lithium ion versus other ion in the system. Higher lithium ion transference number improve lithium ion transport and battery performance, and we find that the optimum co-solvent content is about 25% and DMSO particular at 25% provide the best both ionic conductivity and transference number. As you can see here, the transference number for the system that add DMSO is higher than other, about 0.47. At 25% co-solvent, the first solution shell around lithium ion varies with types of co-solvent, and DMSO result in lithium ion coordinate with 1 EC and 5 DMSO. This structure forms a distinct structure with no PF6 anion in the first solvation shell, and this structure can alter the solvation dynamics. So the key takeaway of this study is like 25% of co-solvent offer the best performance for enhanced ionic conductivity and can improve the lithium ion transference number, with the DMSO showing the most promising performance. So let's move to the development of cellulose-based solid-state electrolyte for lithium-sulfur battery. Lithium-sulfur batteries offer high capacity at lower cost compared to lithium-ion battery with abundance of sulfur and no toxic metal. Unfortunately, challenge like lithium dendrite and the polysulfide shuttle need to be addressed. So main issue in lithium-sulfur batteries include lithium dendrite growth here, and this can make a short circuit and system failure. And another one is shuttle effects. That is the dissolution of intermediate lithium polysulfide species in the electrolyte system, and this leads to irreversible loss of sulfur. So solutions include solid-state electrolyte and additives to stabilize lithium cycling. In this work, the goal is to prepare composite cellulose-based solid-state electrolytes or SSE to resist dendrite penetration and prevent polysulfide crossover. We prepare the composite solid-state electrolyte and test via EIS, the conductivity test and cycling test, or GCD here. And there are like two different systems. One is LIEO, is a lithium TFSI in polyethylene oxide or PEO. And another one is we add cellulose nanofiber in order to enhance the mechanical properties. And we also modify the conductivity by applying some additives. And we find that by adding additive, namely acetylnitride, we significantly enhance the ionic conductivity. However, there is the limitation of adding acetonitrile. The maximum amount of acetonitrile is about 30 milliliters. If we add too much acetonitrile, it can cause the phase separation and reduce the electrochemical stability. From the result, we pick the ratio of lithium and EO at 1 per 16 and 1 per 18 at 30 milliliter acetonitrile for using in carbon nanofiber composite as it show the better conductivity. We found that adding carbon cellulose nanofiber and other additives to PEO, we can improve the lithium ion cycling from the result here. And in addition, testing for mechanical strength via UTM test, the results show that cellulose nanofiber increase tensile strength. We obtain the tensile strength about 24 megapascals. The key takeaway from this work is like higher additive content increase conductivity and enhance lithium cycling, and carbon cellulose fiber can increase the tensile strength, which help inhibit dendrite growth and prolong battery life. And the output of this work is like we have successfully submit two manuscripts. Thank you for your attention. Any
Now
questions?
we are welcome question from the floor.
Thank you very much. I understand lithium and the sulfur system has high potential for the battery, but there is issue
Yes.
about the life cycle.
Yeah, the cycle life.
And in my understanding, the reason why is sulfur
Polysulfide, right?
into the electrolyte and shorten the
Yeah.
life cycle. And my question is, that issue is much improved in your developed material.
Yeah.
Is it correct?
Yes, it's correct. Yeah, we try to develop material that can resist the dendrite penetration because the dendrite gonna grow like this, right? And then
Dendrite
the
precipitation.
system failure, short circuit like that. So we need to make the materials like harder with a high mechanical strength while we mix with nanocellulose fiber.
Okay,
Okay.
I understood.
Yeah.
I think it's very excellent result. Thank you very much.
Thank you.
Any other questions? If not, I may have some question. So your first work is based on simulation.
Yes.
Did you do experiment?
Yes,
to
we also like do some experiment, but that work is like done by NTech. Yeah, we combine.
Did it give the same agreeable result with the
MSO.
calculation?
Yeah, the MSO is better than other co-solvent because the MSO.
And at that ratio,
Yeah, at this ratio. Yeah.
Okay.
We not do all ratio. We like just compare at 25% and compare with 4 co-solvents, and the MSO show the best performance.
Oh, so you did one. Just one.
Yeah,
Okay.
the main job is about simulation.
And according to the previous question, did you try to characterize that the additive that you add really prevent that dendrite growing, or
The additive is kind of like add to enhance the electrochemical properties, yeah, but not about how to say,
But
not about the
what-
dendrite growth like that.
so what prevent the dendrite growing?
We try to prevent the dendrite, like also electrolyte is the main part, yeah, but also like the mechanical strength also important.
Yeah, but
like
did you like characterize that no
No,
dendrite growing?
from now we not characterize the dendrite.
Okay.
We just characterize the performance of battery
Okay, so
via
based
cycling.
on the performance and hypothesis.
And conductivity, like very simple one. Yeah, maybe in the future. Thank you very much, Professor.
Okay, so we move on. If there's no other question, any? No? Okay, we move on to the second presenter. Thanks. Okay, our next presenter is Associate Professor Dr. Patsavi Jansuk from the Faculty of Pharmaceutical Science. His topic will be on the development of imatinib cyclodextrin complex loaded surface modified PLGA nanoparticles for targeted colon cancer therapy.
Good afternoon, everyone. So first of all, I would like to change my presentation titles because of the ingredients that's used in for the PLGA that is not coming yet when we are starting with the projects. So then we try to use the other nanotechnology platforms that we can cause using the neosomes. The neosome is a vesicular systems that, and then we use that to use for the cells that lung cancer therapies. So here for the WHO that can report that the lung cancer is the leading cause of the cancers and the deaths of the worldwide. Approximately 1.8 million people die from the cancers in annually. So from the lung cancers, we have two kinds of the lung cancers. One is a non-small cell lung cancer, another one is a small cell lung cancer. So most of our 85% that from the cancer, lung cancer, we report that is a non-small cell lung cancer. And the predosing factor from the non-small lung cancer is from the smoking. So smoking is the main cause, and not only from the smoking, but also from the secondhand smoke that have a risk factor of the lung cancer as well. So it is good that the community to introduce from the smoking cessations to awareness how to decrease the risk of the cancer from the lung. From the treatment that we can use like many medicines, one of them is a tyrosine kinase inhibitors that for specific genetic mutations that can use for the booster the survival rate and the quality of life of the people who suffer from the lung cancers. But imatinib, that is the compound that we use to treat in the lung cancer. It is one of the tyrosine kinase inhibitor that approved for the treatment of the leukemia and the GI tumors. And IMB have to inhibit the non-small cell lung cells cancers that can hold dose dependence with the IC50 around 2 to 3 micromolar. But unfortunately, that imatinib have the very low solubility. It is practically insoluble in water. Only is 0.01 milligram per ml. So then we need to have the techniques to solubilize the imatinib because it's the water insoluble. One technique that we use the cyclodextrin. Cyclodextrin is the oligosaccharide that is composed of the glucopyrronic units and have the shape like this. So the inside is the hydrophobic cavity. So the outside is the hydrophilic. So when the drugs can go to the cavity of the cyclodextrin, it can form water insoluble complex that can increase the solubility of the drugs. And another one that we use the neosome is the vesicular systems. So neosome is composed of the non-ionic surfactants. So the composed of the hydrophilic heads and hydrophilic tails. It can be self-assembled into the media and then can form like the bilayer. So the insides that you have of the hydrophilic inner core that can encapsulate things for the hydrophilic molecules. And the bilayer have the can encapsulate for the hydrophobic materials also. So then the neosome that can have ability to prolong the circulations of the entrapped duct, minimize of the duct degradations, and can be used into the human bodies. So we use two techniques together with the drug in CD in neosome. It's like a complex strategy. So we need to use the encapsulated drug molecule itself and together with the water-soluble complex. So for the enhanced the aqueous solubility of the drugs can be lower leakage for the lipophilic drug molecules from the neosome like bilayer and better control drug release profiles. So in this study, we would like to, we study with the complexation of the imatinib with the various cyclodextrin, and then prepare the neosome with the encapsulate of the imatinib with the cyclodextrin complex to develop and then characterize with the physical-chemical properties. And then investigate for their cytotoxicity, cellular uptake, and apoptosis to the cell lines. Here is the first study. We study the solubility determinations first. We use the many kinds of like the cyclodextrin, the alpha, beta, and gamma. It's different from the number of the glucopyranose units. It can form 6, 7, and 8. So gamma cyclodextrin is the largest cavity. And then we also use like the hydroxypropyl gamma cyclodextrin. It is the derivative ones. Then we have like to show the slide, the figure that when we increase the solubility, the concentration of the cyclodextrin, it can be increased solubility of the imatinib. And among from the natural cyclodextrin, gamma cyclodextrin is the best one that is from the largest cavity that can have like the compensation efficacy and stability constants higher than beta and gamma. And also from the hydroxypropyl gamma cyclodextrin with the derivative one, so it should be the highest one. It is the best solubilizations. So then we confirms that the solution state characterization by using the proton MMR. So normally that when we study the Eastern complex, H3 and H5 should be chemical shift when include the drug into the cyclodextrin cavity. So the H3 is about like the higher can increase like the chemical shift of the protons. And also for the outer proton from the cyclodextrin can increase, enhance the stabilizations by changing the chemical shift as well. So this is the molecular docking that can confirm that the solution state by proton NMR that the drug can inside the cavity of the cyclodextrin. And now shall we go to the preparations of the neosome. So we use a thin film hydration methods. All materials that are stabilized into the chloroforms and then keep in desiccator form after evaporated. And then we use the hydration medium that composed of the IMB and the cyclodextrin. We have four formulations that's according to the gamma cyclodextrin and then the HP gamma cyclodextrin, and also in the presence of the TPGS. TPGS is like the condition enhancer for our hypothesis. And then we study with the physical-chemical properties. So the physical property can show in this table. When we add the TPGS into the neosome, it can decrease the particle size and also from the increase the present encapsulations. And now that for the morphology, we can show that is for the SEM that from the imatinib without the TPGS, and with the TPGS that can be shown the smaller particle size and look like the fluidity from the textures of the morphologies. Here is the cytotoxic study that we use our formulation to test it with compare with the free duct in the PAS and with the blank neosomes. And we show that our formulations and have like the concentration dependent. When using the higher, then the cytotoxicity is higher. So the most optimum one is like the hydroxypropyl gamma cyclodextrin with the interpresent is the TPGS that can significantly to increase the cytotoxicity to the lung cancer cells. And the next one from the cellular uptake, so we use like the FISC instead of the drug and then use the same neosomes and then to see with the relative intensity of the feces. So we show that our formulations can be better when compared with the non-treated, and then can increase the cellular uptake of the feces into the cell or the lung cancer cells. And the last one is for the cell apoptosis. So we can show that in our formulation, especially for the neosome with the hydroxypropyl gamma cyclodextrin in the presence with TPGS, it can be have like the high edge for the apoptosis. According to the present with the untreated one. So it's about 35% with you treat with the 5 micromolar and 85% apoptotic cells about when we treat with the 10 micromolar. So overall, the results that can show that we can improve the cellular uptake and then can promote that imatinib-induced apoptosis with when we increasing with the cyclodextrin and the TPGS in the neosomes. So overall, for the conclusions, the gamma cyclodextrin and hydroxypropyl gamma cyclodextrin can enhance the stability of the imatinibs. And we can develop the neosome with the suitable physical chemical property. And in the presence of TPGS, that we can say like the penetration enhancer can increase the efficacy of the drug into the cells. And furthermore, that we need to study with the in vivo study to deeper understand for these effects. So I would like to thank the Asahi Glass Foundation for the supporting the grants to my projects. Thank you for your attention.
You're welcome. Question from the floor.
Hello. Question.
Hello.
My question is fundamental, just for my own confirmation of your experiment. You are trying to form complex of the imatinib drug with water-soluble cyclodextrin molecule.
Yes.
Once it is soluble, you try to encapsulate them in some nanoparticles.
Yes, in the ozone.
As a for drug delivery in a.
Yeah.
Okay, I see. So my next question is, how did you arrive at this idea of cyclodextrin to form the complex, then this specific PLGA nanoparticle? Is this from an ongoing research of your group for this material, or you got the idea from other research?
They have like the review literature also from the drug in the CD in liposomes, but the CD in the neosome is like look like a more novel that can be using it. So liposome is another type of the vesicular system. So then I use neosome in my lab.
I see.
Yes, and then I developed the cyclodextrin into the neosome. This is like cyclodextrin complex is my expertise to use it also. And then for the neosome, we need to have like the nanoparticulate. Like a lipid, when we go to the cells, they have lipid exchange. So they have like two strategies together. Yeah.
Right, thank you for your explanation. My suggestion is to, maybe for your next paper, take a standard literature method for colon cancer delivery and then compare. Just a suggestion.
Yeah, okay, thank you.
Thank you.
Because I changed the types to the cancer. Now I changed the type to do the lung cancer. Yeah, the previous proposed that we use like the colon cancers. So the another type. Yeah.
Okay, thank you.
Thank you very much.
Thank you very much. I think you got many useful data in vitro. And do you have any plan to confirm your result in vivo by using animals or in the future?
Yeah, I not to plan yet, but I would like to ask for the collaborations to study more for this kind of that.
If so, this is my own opinion.
Okay.
We'd like to support as Asahi Glass Foundation. Thank you very much.
Yeah, okay. Thank you very much.
So maybe one quick question.
Okay.
So experimentally, after you incorporate the drug into psychodextrin,
Yeah.
how did you measure the percentage of incorporation?
We use indirect the methods by using the centrifugations and then the nanoparticle with the ultra
No,
centrifuge.
just I mean psychodextrin.
Psychodextrin complex.
Yeah.
We use HPLC to analyze.
Also use SPLC.
HPLC,
Okay.
yes. To analyze the complex from the phase 3 profile, yes.
And for the nanoparticle,
Yeah.
you use a centrifuge.
Yeah, use centrifuge and then
measure
indirect
the solution.
measure the supernatant and then minus in the equations.
Okay. Any more question? If not, let's thank the speaker, and we will welcome the next speaker as well. Okay. Our next speaker is Assistant Professor Dr. Intouch Hong Ratana Vichit from the Faculty of Science. His topic will be on the preparation of antimicrobial and biodegradable cellulose nanofiber hydrogel from agro waste for sustainable active packaging in fresh meat application.
Thank you, Professor. Okay, good afternoon, audience. My name is Intouch Hong Ratana Vichit. Okay, today I would like to talk our research. So next to the introduction, according to the survey conducted by the Department of the Pollution Control Thailand, as you can see in this pie chart, the results show that in the year of 2021, the quantity of food waste account as much as 64% of the total waste in Thailand. This amount approximately 20 million tons per year. So from this waste, Thailand managed to the landfill, resulting in pollution which generates odor and contribute to the accumulation of the disease. So in our research, we have discovered that one effective method to reduce food waste is using the active packaging. So the active packaging refers to the packaging materials that can interact with the product and the environment inside the packaging, leading to the subsequent benefits. So the active packaging can also extend the shelf life of food and ensure the safety of the customer, promoting the better quality of life and well-being. In this study, we utilize the hydrogel, which is commonly found in meat packaging and serve the purpose of absorbing the meat extruded. Moreover, we modify the hydrogel to release the antimicrobial agent. In this research, we use the silver nanoparticles. Talking into the consideration of the environment sustainability concern, to achieve this one, we replace the petrochemical-based polymer with the biodegradable polysaccharide, namely cellulose, for produce the hydrogel. So our objective are to study the method of the preparation and development of the antimicrobial hydrogel from cellulose nanofiber for active packaging application, and to study the properties of the nanocellulose hydrogel with the different amount of the silver nanoparticles. Let's move to the experiment. The experimental procedure for preparing cellulose nanofiber from coconut husk waste. Briefly, we got the coconut husk waste from the coconut farm in Prachuap Khiri Khan province, Thailand, and the coconut husk waste then cleaned and passed through the alkali treatment and bleaching process to become the cellulose fiber. And then we disperse the cellulose fiber with the DI water to achieve the condition about 0.5% weight by volume, and then we transfer the cellulose through the high pressure homogenization process at 20,000 psi for 12 cycles. So the high pressure homogenization will reduce the diameter size of the cellulose fiber to become the cellulose nanofiber, as you can see in the FESEM in this picture. So next we will prepare the nanocellulose hydrogel by mix the three solutions together, which is the nanocellulose, approximately 0.5% weight by volume with the sodium alginate and glycerol. And then we incorporate the different concentration of the silver nanoparticle at 0 pHr, 0.008 and 0.015 and 0.030 pHr. Then we remove any air bubble from the mixing and place into the PP mold. Then we cross-link with the calcium chloride. So finally we will got the active hydrogel, which in this work we call AGH. So next we test in various kind of characterization. The first one is the FESEM to examine the surface morphology and element composition of the nanocellulose hydrogel, antimicrobial activity, cytotoxics by MTT assay to evaluate the toxicity of the nanocellulose hydrogel toward cargo-2 cell line. And the last one is TVBN analysis to quantify the amount of the volatile nitrogen compound, which indicate the spoilage of the meat products. So let's move to the result. The first result is from the FEM testing. The FEM image we observe at the magnification of the 20,000, and it reveals that in each concentration, the cellulose fiber appear as a dispersed nanofiber interwoven together, like the mesh, like in this structure as you can see in 4 pictures. In addition, there were a silver nanoparticle distributed throughout the sample. If you can see in AGH 0.008 to the AGH 0.030. And however, we observe that at the high concentration, the accumulation, as you can see in the late cycle, occur. So we confirm again by the EDX mapping, which show that in the 0 pHr, the silver nanoparticle not present in this structure, and it observed that as the concentration is increased, the mapping in this picture, as you see, the mapping will present the silver nanoparticle like an orange dot in 3 pictures. And again, in this picture of the AGH 0.030 pHr show the accumulation of the silver nanoparticle as agreed with the FESEM image. So the antimicrobial activities in this image show the colony in the front column with refer to the 0 pHr. The colony refer to the alive bacteria, and the other plate watch not show any the colony. As you see in this table, in the front row of the AGH or the gel without silver nanoparticle, in both gram S. aureus for the positive gram and E. coli from the negative gram. After past 24 hours, the increment of the number of the cell was present. And if we observe the gel with the addition of the silver nanoparticle at all concentration, it can be observed that the effective inhibit bacteria growth by 99.99%, if you can see in this one. This is because the particle can encounter the cell membrane, and also it can pass to in the cell with it can react with various kind of the molecule and functional group inside, leading to inhibit the bacteria growth and causing damage to the cell. So the cytotoxic test we conduct to test to measure the toxicity, as I said that we use the cargo-2 cell line, which represent to the intestinal epithelial cell. So the standard specify that the toxics occur when the cell survival rate is less than 20%. And if you see in this table, the increasing of the silver nanoparticle provide the decrease in the percent cell viabilities. And if you see that at the high concentration, the cell viability is less than 70%, that means it's already toxic. So we have chosen the concentration about 0.015 pHr for TVBN test, which will be conducted on the fresh meat. So the last one is the TVBN test. This test is measure the spoil rate of meat based on the volatile nitrogen compound. In this research, we select the chicken meat as the raw material due to the high consumption in Thailand and also in the global. So in this work, we divide the storage method of the chicken meat into the three categories, which is the blank or black line, as you see in this graph, refer to the chicken meat without any preservative treatment except keep in the refrigerator. The CNFH or the red line refer to the chicken meat preserved with the hydrogel without any of the silver nanoparticle. And the last one is AGH or blue line, refer to the chicken meat that preserved with the hydrogel containing with the silver nanoparticle at 0.015 pHr. So if you see in this graph, at all storage time, we observe the increase in TVBN, and at the day 10, the blank sample start to show the sign of the spoil rate refer to the TVBN value exceeds than 25. And moreover, we found that the AGH consistently had the lowest TVBN in every day, as you can see in this blue line. This is because the hydrogel have the silver nanoparticle that can inhibit the bacteria growth. And if we consider to the freshness level 1 in the in the value of the TVBN lower than 15%, it show that the blank have the shelf life about 3.9% and CNF for 3.9 days and CNF for 4.2 days, and the base condition is the AGH that have a longest shelf life about 6.4 days. So the conclusion, we are success to prepare the cellulose hydrogel which coupled with the silver nanoparticle, and the condition about 0.015 pHr is the best condition for use as the active packaging because it can inhibit both gram bacteria compared with the cargo-2 cell line and extend the shelf life. So finally, we would like to thank you, the Asahi Glass Foundation, for support us, and thank you very much for your kind attention.
Question?
Thank you very much. I understand well your developed material has very excellent performance of
Antimicrobial.
Yes. Yeah. But my question is, for instance, AGH 0.015 have enough mechanical properties and transparency required for, as you say, as packaging material.
Okay, for the mechanical property, it's unfortunately about this research that the mechanical property is not quite well because the it have a lot of the content of the cellulose nanofiber and less of the binder. So in this work, we use the alginate like a binder and like a polymer that form the hydrogel. So for the next research that we already study about the hydrogel, we use the high molecular weight biodegradable polymer to incorporate with for promote and and improve the mechanical properties. And for the opacity of this work, as you know that the silver nanoparticle have not much clear particle. If we cooperate with the hydrogel quite have like a little bit gray color. So if we use just like a pad that placed under the meat is okay because the customer doesn't see it. And or you can use like another secondary packaging to cover the hydrogel. It can be used. Can be work as well.
I'd like to confirm the appearance is not the transparency, but the kind of translucent.
Yes.
Understood. Thank you very much.
Any other questions? Okay. A few questions. From your presentation, when you use less in the lab, when you use less silver, like I think it's 0.008, you also have like 100% antimicrobial in the lab.
Yeah.
So why do you choose to use 0.015 instead of 0.08, which will cost a lot less and still effective?
Okay, this is a good question because we already use the 0.08 pHR to test the TVBN and the result showed not quite good enough when we use in the practical with the
real
meat.
meat.
Yes, because maybe the real meat have many of the microorganisms, so it may be not work. So we select the 0.015.
That also lead to my second question. How did you test with the meat? Did you wrap it all over or just put it underneath?
We just only put it under the meat and we use the meat approximately 100 gram with the hydrogel diameter size 8.5 centimeter and 2 millimeter of the thickness. 8.5 centimeter and the thickness about 2 millimeter.
So it's not covering the
Not
the
covering,
whole meat.
yes.
But normally when you do packaging, you cover the meat, right? So it may work.
We aim to use just like a extruder pad to replace like an absorber pad in the meat in nowadays because the absorber pad in nowadays doesn't have any of the antimicrobial property, so we aim to replace that one.
So, but wouldn't it a lot more effective if you use it as a wrapper and use less silver? Which one will cost less anyway?
For I think in the real situation, if you buy some meat that have something cover them, maybe the customer will have a lot of question. What is inside? What is look like inside? So if we use like a absorber pad that we use in the real situation, so maybe the customer will not have much doubt, and the industrial will like industrial will like to use like a absorber pad because they didn't have to modify the process.
The film.
Yeah.
So you think it's a lot harder to put your material into the film, the thin film. It's easier to put in the thicker pad.
Because this one is not like a thin film, it's just like a hydrogels.
I see.
So it's aimed to like absorb some of the extruded from the meat.
Okay, thank you very much. So I think if there's okay, one more question.
I have some question. First of all, thank you for this this research. Aiming to extend the shelf life of the fresh food is quite an excellent application. I happen not to see that what my first question is that what is the working temperature for this hydrogel? Because normally when we use it in the hydrogel pad in the supermarket, we place into the some kind like open fridge, right? So the working temperature should be quite wide enough. Whether it is kind of like in the cold temperature or in the room temperature one to store this mechanical this antimicrobial or property. So what's the working temperature for this hydrogel?
So in this one we work in the refrigerator temperature about 6 to 8 degrees Celsius. I think it can work, but not much. I'm not sure about the efficiency of the antimicrobial in the room temperature, but in this one we use in the refrigerator.
I have one more question. There was you showed a slide about your CACO2 cell analysis. Could you explain in simple what is the significance of that test?
Because for this one we use like as an active packaging for the food packaging. So I need to make sure that if it leave with the food and we take it inside the body, it will be safe because the CACO2 cell line is representative like a intestinal epithelial cell or the cell in the intestine or in the body in the gas in like a colon of the cell.
Okay, I get it. Yeah. So that test is trying to quantify how toxic it is to humans if we choose to eat everything.
Yeah.
Okay. Thank you.
Any more questions? Seem like interesting, right? A lot of questions. So, if there's no more question, I please join me thanks the presenter. And I think we run ahead of time quite a bit, and our next presenter cannot be here today, but I believe we have a video recording from her, right? Dr. Rong Chachalan, we have a setup ready to present. Her topic will be in green synthesis of potassium vanadate utilizing Tamarindus indica extract for application in rechargeable battery.
I'm Rong Jajaran from Metallurgy and Material Science Research Institute of Chulalongkorn University. Today, I'm quite happy to share with you my work on batteries, which I got sponsored from the Asahi Glass Foundation. So let's dive into my work. So the work I got funded from the Asahi Glass Foundation was on the green synthesis of potassium vanadate utilizing Tamarindus indica shell extract for application in rechargeable batteries. So the reason why that I start this work is that there's a increasing demands on batteries from all kind of application, from consumer electronics, for the stationary application, as well as transportation, as we trying to move towards e-mobility. But that really requires increase in battery manufacturing as well as implementation. But the current technology is mostly based on lithium, and it has quite a few limitations. First of that is the safety. It is also kind of toxic, and there's only limited resource of lithium around the world, where we can only found in certain countries. So this really motivates development of alternative battery technology, which in this case I propose to use zinc-ion batteries. Let's go through this a little bit. So the good thing about zinc-ion is, as I said, is much more abundant. Like you can find zinc and you can find manganese quite easily in many places as one of the few earth abundant materials. And considering the cost of the active material, like for the anode part, the cost of zinc is much lower than lithium. Let's see here. much lower than lithium, and the cost of the cathode materials for zinc ion battery, even though for the manganese and for the vanadium, they are still low, much lower, like 10 times lower than the cathode materials for lithium. And also it's quite safe, as we can use the aqueous electrolyte, and we can also make it fabricate everything in ambient. And once you make this, like, since it's very safe and it's like non-toxic, so this really would open up many applications, including, you know, the portable electronics, where in this picture you can put it on, like, you feel comfortable putting this on your arms, on your hands. So that's why we should dive more into this. However, the conventional cathodes, as I said, like, there's like the conventional cathode for zinc is like either the manganese or the vanadium. Of all those two, vanadium V2O5 is much more interesting if you want to develop something that can charge very quickly. So if we talk about, like, okay, we there's an urge to develop like a battery for electric vehicles mobility, so we have to think about how to make zinc and vanadium based battery works well. But the thing is, there's a problem with this V2O5 structure, as the crystal structure is a layer type. So then that as the zinc ions go in and out during the discharge reaction, this structure could collapse, and that would lead to a loss in capacity of the battery. So the cycle life is not that long. So there's been some thoughts on like try to incorporate some larger ion. For example, this case, like potassium, which has a larger ionic radius compared to zinc, into this layer, in between this layer structure, such that, say, you think about it, like if you put the potassium ions there, that it kind of like opened up the structure, and that would make it easier for the zinc to go in and out. And since like it will be a little bit ionic, like this ionic potassium would kind of like bonds it and kind of like make it more stable. So this is one of the idea where, in this case, like in this work, like we try to develop the potassium based potassium inserted vanadium VOX materials for batteries. But thinking about it, so I look more into how the people usually synthesize the potassium vanadate. Usually people synthesize it at quite the synthesis takes quite long. Like the temperature required for this synthesis is above 180 degrees Celsius for more than 24 hours. And after this, you also need to do some calcination to get a good phase. While in this work, we propose to use a waste from agricultural, like in our country, we actually export a lot of tamarind. And that, like, tamarind is a good source for both the organic, and it's also for potassium, as we have, like, as in tamarind, that's quite a big chunk of potassium. So in this case, we propose to just like to lower the lower amount of energy required to synthesize the potassium vanadate cathode by doing a green one pot synthesis at the temperature below 110 degrees Celsius, and with the time of the reaction below 6 hours. So the concept would be using this potassium and organic form tamarind shell extract, and then kind of like use this organic to assist the synthesis, which is not a hydrothermal, but would be more towards like a soil gel and precipitation methods. So the way we do it is that I took tamarind, and I actually order, like, so after tamarind seasons, we could order a shell, many jars of tamarind shells that's kind of like crusty already, and then we go through this. So this is like one. So this is after we we put it in the blender, but then we have to do it more and more, and then we get the fine powder like this. In this project, we investigate two different ways to extract the organic and potassium from tamarind. One of them is a water base. So in this case, we put the tamarind shell powder in a tea bag, and then we boil it or like heat it up at 80 degrees Celsius for like as however long you put your tea. But in this case, we do it for like less than 1 hour, like maybe 10 to 30 minutes. And then after that, we filter it out, and then we use this as is. So this water-based extraction is good, as it actually gave us better results in terms of we get both potassium and we get both organic. But the thing is, we cannot really stock this extract. So we have to do like a fresh batch every time before we do the potassium vanillate synthesis. However, we also explore another way where we can, like extract the chemical from tamarind in advance. In this case, we just put we put the tamarind powder in the ethanol solution, and we kind of like let it soak there for a day, and then we keep collecting this this ethanol solution, and at the end we take it to the rotary evaporation to get more I guess like more concentrated tamarind extract. In this case, of course, like after we get this, we can keep it in the fridge, and then we can use it whenever we want to do the battery material synthesis. But the problem is like we didn't find the source of potassium in this case. So there's a trade-off between the two methods. So we think that if we want both the potassium and the organic, so we should probably go with the water-based extract. So we take the water extract and go further into the synthesis. But first, let's explore, so first we do the phytochemical testing of the water extract and the ethanol extract of the tamarind shell. And it's quite similar that, even though the amount of potassium are different, but in two cases, we found the alkaloids, we found tannins, and we found phenols. So if you don't care too much about the source of potassium, these two ways of extraction would be okay to obtain a, would be okay in assisting the synthesis of the potassium vanillate. And then we did further into we took this extract and measured the GCMS, and these are the five highest concentrated chemicals that we found from these extracts. It's quite common. They are quite similar to each other, regardless of the way we extract it. So once we have this extract, then we do this green synthesis where we put this in oil bath at a temperature around 100 degrees Celsius, and put the vanadium precursors, and then we put the extract, and then we kind of like let it stir, and then once we get the precipitates out, then we take this precipitate and then we do calcination at a temperature around 500 degrees Celsius. And we think that there's like from reading papers, there's some effect of the pH during synthesis. So we explore like with the pH adjustment during the synthesis, and looking at the morphology of these cathode materials, you found that like for the picture A, that's like we didn't control the pH. We just like put everything as is and do the synthesis. This one seems to give us quite a good like nano wire shape, but it's quite random. But when we do a pH of 3 or 5, like the size of it seems to increase a little bit as we increase the pH a little bit more. But it's interesting to notice that like the phase that we got for the pH 3 and 5 are quite similar. The only difference is the morphology. While if you compare with the control, like the phase that we got for the control different ones. So see here shows like first message is that the pH during synthesis is kind of important to control whatever phase that you would get out from your cathode materials. And then we go further into explore the electrochemical behavior of this cathode material. So we mix the cathode materials with the conductive carbon and binder, and then we put into a coin cell like CR2032 in a zinc sulfate electrolyte, and then when we measure the cyclic voltammetry. And we found that the oxidation and the reductions for the pH for the control one, it's slightly different, of course, because it's different phase, but there are more numbers of redox reactions for the control as compared with the one synthesized at a pH of 3 and pH of 5 here. But these two are quite similar, but the 5 one seems to be slightly better in terms of the reactions. So as expected, when we go further into battery, so actually for the control one, it didn't work at all. This phase, like it didn't work well as a battery, but for the one at the pH 3 and for the cathode material that we synthesize at pH 3 and 5, it seems to work as a battery. This one we do the galvanostatic charge discharge at the current rate of 1 amp per gram, and it gave us a good capacity above 100 milliamp hour per gram for both cases. But the one that synthesized at the pH closer to neutral, like pH 5, seems to be better in terms of both performance and stability when we look at this graph B. So this one, in conclusion, this work really shows that the tamarind shell extract is beneficial for a green synthesis of KVOX, and it's possible to synthesize this way at a much lower temperature and much shorter time. So it's more energy saving so that we can produce more and more materials. Second point is that the potassium vanadate synthesized at pH of around 5 seems to be the best cathode materials, as it has quite high activities in the cyclic voltammetry graph, as well as it yields like the highest discharge capacity of 130 milliamp hour per gram, and the cycling stability over 40 cycles. So that's all for my talk. Thank you so much for all your attentions. And if you have any questions, please feel free to send me an email. Thank you.
Okay, so the presentation has ended, and unfortunately the presenter is not available for question and answer. So we will move on to our next presenter, which I noticed is she's already here, Assistant Professor Dr. Benjaporn Narupai, and her topic will be on 3D printing of non-drying, stretchable, self-healable ionic conductive hydrogels for wearable sensors.
Oh, sorry. Hi everyone, I'm Benjaporn Narupai from Chemistry Department, Faculty of Science,ฬาลงกรณ์ University. And today I'm so excited to talk about my work on 3D printing of conductive hydrogel for wearable sensor. Stretchable conductive wearable sensor can be used in a variety of applications. For example, it can be used in healthcare monitoring devices, or it can be used in wearable electronics or even strain sensor to track various human motion. In this study, we interested in using kappa carrageenan as a main material because it is a polysaccharide that derived from red seaweed. In addition, it offers biocompatibility and biodegradability. It also contains 15 to 48% of the sulfate group, which can induce the ionic conductivity of the hydrogel. However, when we use the kappa carrageenan as a hydrogel, we always have a problem with the poor mechanical property, like Dr. Intouch presented earlier. So we cannot use that hydrogel to use as a wearable sensor because it has poor mechanical property. It's so fragile and it's really brittle. So we need to improve the mechanical property. We need to find a way to do that. And one of the techniques that people usually do is to make it as a double network hydrogel. So when we make a double network hydrogel, we can improve the mechanical properties significantly. So this is based on two mechanisms. So, okay. So this is based on two mechanisms. When you apply the force to the hydrogel, the first network will be broken first under the deformation and absorb and dissipate energy. And then we have the second network that still hold on to the hydrogel network. So when people prepare the double network hydrogel, they usually use the traditional fabrication method, such as molding or using the casting method. So this can limit to the 2D patterning. So if we can print something that is more complex and can fit for an individual, it can improve wearable comfort and also improve the sensing performance. So why don't we use 3D printing technology? Because 3D printing can print complex architecture. It can print some customized objects, such as the hearing aid that can fit perfectly for your ear, so it can improve wearable comfort. In addition, 3D printing is a rapid prototyping. We can print 1,000 of swabs for COVID-19 tests within like half an hour. So in this project, we aim to use 3D printing technology to print a conductive wearable sensor and using the kappa carrageenan as a main material. So in this case, we also add the hydroxyethylmethacrylate and acrylamide as a co-monomer. We also add the puronic F127 bisurethane methacrylate as a cross-linker. We also add the photo initiator in here to initiate the polymerization. So at first, we mix everything here in water crystalline surface, solvent at high temperature. And then at that point, the F127 here will transform to the micelle structure. And then after that, when we cool it down to allow 40 degrees Celsius, the kappa carrageenan will form the helical structure like this. So at this point, we can use this to 3D print and make a complex architecture. And then after that, after we get the 3D print structure, we shine the light, and this light can initiate the polymerization to cross-link the polymer network. And then after that, we soak that hydrogel into the iron chloride solution in order to incorporate the iron into the hydrogel. So if you look at this, network, you can see that we have a lot of cross-link in the network. The first one is a physically cross-link from double helix from the kappa carrageenan and also the micelle structure from the F127. We also have the chemically cross-link network from the monomer and the cross-linker. We also have the ionic cross-link coordination between the sulfate of the kappa carrageenan and the ion here. So from this cross-link network that we have, it can improve the mechanical property of our hydrogel significantly. So before we can do the 3D print, we need to determine the temperature that we use to print. So we have to perform the temperature sweep experiment where you plot between the modulus versus the temperature. So you can see that at high temperature, the mixture is liquid. But then when you lower the temperature down at 40 degrees Celsius, the mixture becomes a gel. So at this point, it will become a gel. And then we will use 40 degrees Celsius temperature as a printing temperature. And here is what the 3D printer look like. It's called direct write 3D printing. So the way it works is that you load the material into the syringe, and then after that you apply the air pressure, and then the material will be extruded out and then deposited onto the surface. So the way it moves or the pattern that they draw is depend on how we program the printer. So basically you can print anything you want, any pattern, anything that you can think of. So they will print layer by layer until they can finish the whole 3D structure. And here are the structure that we have print. We print a butterfly structure. We print a complex cylinder, even a cone structure, or even a more complex structure such as a lattice structure or the auxetic structure here. So you can see that we have the ability to print a complex architecture here. And one thing that the hydrogel always have problem is the dehydration behavior because that hydrogel have a lot of water, right? When you leave it on the bench, the water evaporates. So what happens is that the hydrogel will shrink and the mechanical property will change as well. And it will affect the sensing performance. So what we do in our project is that we add the glycerol into our hydrogel. So what happened here is that glycerol can prevent the dehydration behavior of the hydrogel. So if you look at this graph, you can see that the mixture that we have the glycerol, we have 70% weight retention. Compared to the one without glycerol, we have just only 48% retention. And if you look at the picture here, you can see that when we have the glycerol in the mixture, you can still see the hydrogel here, right? And then without the glycerol, you can see that it shrinks a lot, which could, affect the sensing performance and also the mechanical properties. So in this study, we aimed to study the effect of the kappa carrageenan on the mechanical property as well. So this graph is a tensile test. So you plot the graph between the stress-strain curve. So at 1.5 weight percent of kappa carrageenan, you can see that we have the highest stretchability up to 1,800%. And then when we increase the kappa carrageenan to 2 and 2.5%, you can see that we can increase the toughness and the Young modulus of the hydrogel. So as you can see here that we have a remarkable mechanical properties of the hydrogel here. So what happened when you apply the force is that when you apply the force during the deformation, the physically closed-link network from the unzipping of the double helical structure will be broken first, and then it can dissipate energy and can prevent the breakage of the main framework from the chemical closed-link network that endure the hydrogel properties. So we would like to use this hydrogel as a conductive sensor. At first, we need to make sure that our hydrogel have enough ionic conductivity. So we also vary the concentration of the iron chloride solution. And then you can see that when we increase the concentration of the iron chloride, the ionic conductivity increased up to 1.5 Siemens per meters. And we would like to test if this is very conductive. You can see that this is a duck bone mold. This is a duck bone that I 3D print. So I connect this duck bone to the LED light and with the battery. After the completion of the circuit, you can see that we can lit up the LED light here. Another thing that I would like to test here is what happened when I stretch the duck bone. So basically, if you look at this equation, you can see that the current is proportional to the cross-sectional area and is proportional to the length. So when I stretch the duck bone, the cross-sectional area will drop, the length increase, and the current will drop. And you can see from here that when I stretch the duck bone, the brightness of the LED light decrease. See? And then when I relax the duck bone, the brightness will go back to the original status. So you can see that we can track the movement here. So what we do next is that we print a strip and then put it on the finger. And then when you bend your finger at different angles, such as 30 degree, 40, and 90 degree, you can see that we can track that. You can see the electrical response in the real times. So we also think that if we can track like a very small change or small movement, and the answer is yes, we can do that too. So we would like to know if it can give us a signal. So we print a strip and then put it on the throat. So when you say something, a word, like for example, hello, 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 it will show you a signal like this in like a real time. But if you say a different word, such as like Asahi, 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 it will show you like a different shape as well. So we also think that, we can detect that. And if you do like forehead frowning, you can also like detect that as well. So you can see that our hydrogel, our sensor have very high sensitivity, and it can track various human motion here. So with that, with that, I would like to conclude here that I have developed a new material that we can 3D print, and we also have a remarkable mechanical properties, and we can use it as a strain sensor that have very high sensitivity to track various human motion. And we also successfully published this paper, and it just online last week. So we get in advanced material technology, and we already acknowledge the Asahi Glass Foundation, and thank you for the financial support, and thank you the Department of Chemistry, Faculty of Science,ฬาลงกรณ์ University, and our group member, and thank you everyone for your attention, and I'm happy to take any questions.
Question from the floor. Seems like easy to understand, right? The work.
Well, you see like visual and video too.
Yeah, just comment.
Yeah.
Very easy to understand. When you stretch the hydrogel, the electrical conductivity drops. In this case, you can exploit this mechanism as a sensor.
Yeah.
And you have shown the
subtle movement.
Throat on the eyebrow. Okay, I can relate to this invention.
Yeah.
So, what is your next step?
So actually, in the proposal, I proposed that it's gonna have like cell-healing behavior, but in this case, we actually try, but it doesn't give us like a cell-healing behavior. So I think the next generation that we would like to do is a cell-healing, where you can cut the sensor, and then after that, you reconnect them, and then it can still like reconnect and then regain like the mechanical property back and the ionic conductivity back. So that is our next step, like the second generation.
Thank you.
Yeah.
Probably, I'm not sure, maybe we probably would like to know what's the real application can be, I mean, in the near future, can be seen in the near future.
Yeah, I think it can use for like sensor for like a sport person to track, like the movement or even patient.
How would it be compared to like what's already have in the iPhone?
Well, you don't have this in the iPhone, Ajahn. Like, we don't have that.
Yeah, but like movement, you said in the sport. What kind? I mean, like you already have the step counting and you already have calorie. What else can you get from this?
Yeah, for example, if you want to see if you squat the right form or not, you can put it on your leg and on your ankle, and then you can like do squats, and then if the signal is on like the right form, you can also track that.
So for training, right?
Yeah, for training.
Have a good good
like
form
sport
of
activity.
training.
Yeah, the performance of like the athlete. Yeah. Or even in rehab, like a patient in rehab that, like if they want to see if after like operation, if the hand can still like working operation like properly. Yeah.
I see. Professor Mungko is trying to think about it from the very average user kind of application for this. I believe that is his motivation.
She said that can be used for like trainer.
Yeah,
to
for
just for
really
athletes.
regulate to see whether how the person exercise in the right position or not. Which is still not
close to everyday use by you and I.
Well, I mean, in the future, like nowadays, people usually hire like a personal trainer. I mean, if we have this, we can probably like see the performance or like, like the performance when you like do exercise or the weight training and things like that. So, yeah. Okay. Like very, very near future though. We still have a lot of things to explore.
Probably it look like a narrow market and require a lot of, maybe you need like artificial intelligence because different person have different
exactly
different body shape as well.
Exactly, that's why we would like to sell 3D printing too.
So it will rely on other technology more than just this sensor.
Exactly.
Yeah, I see.
Yeah. Well, our 3D printing technology can print some, object that can fit for an individual, like a hearing aid that can fit perfectly just for you, not for other people. So it can improve wearable comfort as well. Yeah, we can also print anything you want, actually.
If there's no further question, please join me to thank the speaker and
Thank you.
okay, we will move on to our next speaker, Associate Professor Dr. Anop Ektarawong, on the topic of crystal defect engineering in metal borine thin films for hard coating applications.
Okay, good afternoon, everyone. Thank you for a very nice introduction. Today, I'm happy to share my work, sponsored by Asahi Glass Foundation. And according to the topic, I'm going to give a talk about the metal boride, but to be precise, it's going to be metal diboride with the chemical formula of Mb2, where M can be any element as listed here. And why? What is the reason that I have been interested in this metal diboride? The reason is that it exhibits the outstanding mechanical property and it has a high chemical and thermal stability, and because of these properties, the material can be utilized as the hard coating material for cutting tools. Yeah, as you can see, this is the cutting tools, and these two can be coated by this compound, metal diboride. And for those who are not familiar with the metal diboride, actually, this compound can crystallize in 3 different phases: alpha, omega, and mu phases, depending on the element that you use in the compound. Among these compounds, actually, the one that I have really been interested in is this TAB2 tantalum diboride. The reason is that there exists some discrepancy between experiment and theoretical simulation in this material system. Actually, this figure shows the ground state diagram of a tantalum boron compound in this binary TAB system. So this dashed line, indicate the ground state line. The points that are lying on the ground state line are predicted to be stable from the thermodynamics point of view. And actually, this figure has been derived from, the theoretical simulation using the density functional theory. So one thing that I forgot to mention is that this work is purely theoretical, okay? So this point here is the composition of TAB2. So if you take a look here in this inset, you can see that this omega phase of TAB2 is the most stable compound as compared to the other two, alpha phase and mu phase TAB2. This is the result obtained from the simulation or the theory. But in experiment, what we really see is the alpha phase. So there is some discrepancy in this material system. And also this Ta2B3, the theory predict that this one should be thermodynamically stable, but we have so far never seen this phase in any experiment. So in this work, I would like to address this issue. So what we did is that some defects might play a role in this discrepancy. So in this work, I study several types of defects in our Ta and B compound, or of this compound. I studied several types of defects such as the vacancy, tantalum vacancy, boron vacancy, some interstitial defect or anti-side defect. But the only defect that exhibit the negative formation energy is the boron vacancy in alpha phase of TAB2. So I take into account this kind of defects in the modeling, and I refine the ground state line of this tantalum boron system. So what I found is that the boron deficient alpha phase of TAB2, where X can be some number like 0.16, 0.20, 0.75, they can lie on the ground state line. And because of the stability of this boron deficient TAB2, we observe the destabilization of the omega phase TAB2 and Ta2B3. And actually, what I found in this work can really explain the discrepancy that I mentioned in the previous page. Okay, but another thing that is very interesting is that when there is the boron vacancy in this alpha phase TAB2, is that we observe the significant enhancement of the mechanical performance in this material system. So, for instance here, where X is about 0.3, this is the concentration of vacancy in the system. So the hardness of this alpha phase TAB2 can increase about 40% as compared to the stoichiometric one. Okay, and we also try to provide the physical reason behind this improvement in the stability and also the mechanical performance of this TAB2 compound. The reason can be explained by the electronic band filling effects or the change in the electronic property of this compound. So this figure shows the electronic density of state for TAB2, and you can also see the local minimum in this material system. In the dots here, the density of state. This point is called the pseudo gap, and it is the point that separates the bonding and anti-bonding state of this material system. So the state with the energy below the Fermi level, which is this vertical dash line, below the pseudo gap is the bonding state, and those to the right of the pseudo gap, they are the anti-bonding state. So for the stoichiometric TAB2, you can see that the Fermi level, which is this vertical dash line, is to the right of the pseudo gap. This means that some anti-bonding state of this TAB2 they are partially filled by the electron. But when there exists the vacancy in this material system, you can see the B2 reduced to B.18 or B1.75. The Fermi level shift toward the pseudo gap, and this indicate the reduction in the number of electron filling the anti-bonding state of this material system, and that increase the stability of the material and also the mechanical performance. Yes, but one thing that we have to be careful is that when the number or the concentration of vacancy increases, you basically have a more number of broken bond in this compound, and that result in the increase also in the internal energy of the system. And actually this thing counterbalance the electronic band filling effect as I mentioned before, and it limit the further increase in, for instance, the hardness. As you can see, when the hardness increase up to this point where X equal to about 0.33, if you further increase the concentration of vacancy, the hardness drastically drop, because you create too much of broken bond, too much number of broken bond in the system. So, and if you further increase the concentration of boron vacancy, at some point you will start, some electron in the bonding state will be removed out of the electronic state, and that will drastically decrease the stability of the materials TAB2. Okay, and I think that's all that I would like to mention in this talk. So if you have any questions, please feel free to ask me. Yeah, thank you.
So now the questions open to the floor.
Okay. Thank you very much for your presentation.
Yes.
But on the other hand, bulk modulus has a bit different
Yes.
behavior.
Well, actually, when we have the vacancy in the system, in particular the boron vacancy, some elastic constant for this material system change significantly, and some of them drastically drop. And that's one, those that drop, the elastic constant will be reflected in the bulk modulus. That's why the bulk modulus constantly decrease when you increase the number of vacancy in the system. But for the bulk and shear moduli and also the hardness, they are related to the elastic constant C33 and C44, and those two elastic constants significantly improve in number when you have a boron vacancy in the system. Yes.
Thank you very much.
Yep, you're welcome. Any more questions?
Okay, I have to admit that I don't understand the basic of this work very much, but based on the application that you think that you said in the topic, that it will be used as a hard coating material
for some
so
cutting tools. Yes.
What kind of property is the most important to have the hard coating material?
Well, one can say that hardness is probably the most important property for this kind of material, for this hard coating application. But when the material has a very high hardness, it can also be brittle. So we need to try to optimize the ductility, the brittleness, and also the hardness, also the toughness, everything. So yeah, and they are related to each other. We need to be very careful when we would like to design the hard coating material, actually.
Impact strength also important?
Yes.
Is it the same thing as a hardness or different taste?
They are a little somewhat different. Yeah. For hardness, is the resistance to the scratching or local plastic deformation when it's impacted by some forces. Yeah. Sorry?
You test for impact or anything related to your materials?
Okay, actually, the result all of the result that has been shown in this talk, they are all derived from the simulation.
Just simulation.
Just the simulation,
okay.
but
no experimental.
No experiment, but actually this work has already been published also in this Journal of Physics material, and we try to compare our result from the simulation with those from the experiment that we could found in the literature, and they are more or less in line with each other, actually. Yeah.
Any more questions? Okay, if not, please join me to thank the speaker.
Thank you very much.
And we move on to our last presenter today, Associate Professor Dr. Warapon Chaikirattisak on the topic of development of novel phage-derived endolysin as an outer membrane penetrating antibacterial against bacterial pathogens in aquaculture.
All right, so good afternoon, everyone. I would like to switch the mood of this session toward more about life. Because we talk a lot about battery and physics as well, right? I want to switch now to know more about life. So our lab, under the name the microbe lab here, has been up and running for almost 7 years now. Our main goal is to deal with this number, 10 million. So this number is technically a very large number, right? And for sure, I would be happy if Asahi funded us 10 million into the lab, but it's almost impossible, right? But anyway, the number that we are currently focusing here is a number of people that could be dead from the superbug infection. Okay, and also this number is predicted to occur annually after the year 2050 onwards. So basically, we have roughly 30 years from now for us and actually for everyone here to get ourselves ready to deal with this horrible situation. Okay, So today I'm going to talk about our work, which I changed the topic a little bit about the mechanism of P-killing, or we can call it in short MOK, in which studying it together with the bacteriophage genomics, it can lead us toward the discovery of antimicrobial molecules that we can use in order to fight back the superbug infection in the near future. So in order to get ourselves ready, our lab has been developing a platform that we called it bacterial cytological profiling, or BCP. This platform can help screen for active compounds that exhibit antimicrobial properties against the bacteria or the superbug. So the principle is kind of easy. So currently what we are looking at here is the bacteria. We stain the bacterial cell membrane in the red color, okay? So basically we can see and tell where the bacteria is and also where the border of the cell. And also we stain the nucleoid or the DNA inside the bacteria by blue color here, okay? And then we just look for the difference between them in order to tell whether or not they are sick or whether or not they are dying, okay? So what we are seeing here, the morphology or how the cell look are substantially different. On your right hand side here, they are sick. They are going to die. You'll see that the morphology of the cell here is substantially different from the healthy bacterial cell on your left here. The cell is a little bit fatter, and also the DNA inside it condensed into the donut-like structure, as you will see right here. And this morphology occurs during the treatment of an antibiotic that kills the bacterial cell. Okay, our platform doesn't stop there. We are trying to correlate all of this morphological change of the bacteria toward the mechanism of action of the drug. Okay, so the benefit of using this platform, we can rapidly identify mechanism of action of any unknown compounds according to the morphology of the bacterial cell that match our database. So based on this BCP database, it has been proven successful in many bacteria, including gram-negative bacteria like E. coli, Acinetobacter baumannii, also Vibrio, and also gram-positive as well, like Bacillus and also Staphylococcus aureus. So then, with this, we hope that we can rapidly identify novel antibacterial molecules in the near future. But anyway, due to the decreased rate of antibiotic discovery, our lab has now turned our direction toward another bacterial cell killer, as we called it, the bacteriophage. So technically, from the picture here, you will see the phage in the green color here. They are viruses that infect bacterial cell. Okay, so then what you are seeing here, there are a lot of the bacteriophage in the green color here. They have the head, or we call it capsid. It keeps all the genetic material of the phage inside it. And then they attach on the bacterial cell membrane down here through the tail part here. In order to start the infection, they'll inject the DNA from the head here through the tail into the bacterial cell. Okay? And once they inject their DNA into the bacterial cell, they will start to hijack and take over all the fundamental metabolic processes of the bacterial cell and use them for their own benefit in order to replicate, making more of the offspring. And at the end here, they'll kill the bacterial cell and be released into the environment. So this mechanism here, during the replication of the phage, they will take over the fundamental metabolic processes of the cell, which is similar to mechanism of action of the drug. We call it here mechanism of P-killing of the phage, or MOK. Okay, and this when our BCP come into play in order to observe two major things. The first thing is that whether or not the morphology of the phage-infected cell is changed during the infection. And secondly, if so, whether or not this morphology here matched anything from our BCP database. Okay, so then here's one of the example of the MOK study of a phage, where you see that during the early infection here, the morphology of the phage infected cell changed a lot compared to the normal cell control here. The cell get kind of circular, and also the DNA inside it in the gray color here changed toward the donut-like structure again. Okay. During late infection here, the phage display another MOK in order to kill the bacterial cell, lysing it, so that their progeny inside the bacterial cell can be released into the environment. So then based on all of this, our BCP database, together with the MOK study, we hope that it can help finding even more antibacterial molecules in the near future, not only from antibiotic itself, but would be also from the bacteriophage as well. All right. So then at that time, maybe like 3 or 4 years ago, it was just a thought that we wouldn't know whether or not it would be possible. So then thanks for the funding from Asahi for our chance to start it working on this project. And then here is a proof of concept where we started from the study of the MOK, and it eventually leads us toward the discovery of an antimicrobial molecules that we can use in order to combat the superbug infection. Okay, let me tell you more about the story. So then in this particular work, we studied the phage named KVP40 here that infect the bacteria Vibrio parahemolyticus. Okay, throughout the MOK study, you'll see that the morphology of the phage infected cell changed toward the rounded structure over time. Okay, you will see that after 60 here, the morphology of the cell in the red color here changed to the rounded structure, which is very different from the rod-shaped cell in the uninfected cell control. So then we can say that during the phage infection, it displays an unknown mechanism of killing or MOK that triggered the morphological change toward the rounded structure. So now we compare it with our BCP database, and we found that the morphology of the cell here is similar to this morphology during the treatment of an antibiotic, mexilinam here, that inhibit bacterial cell wall synthesis. So then altogether here, we have a readout that the phage during the infection here, it target cell wall of the bacterial cell, similar to this mechanism of the drug during the late time point after 60 minutes. Okay, so due to this readout, we look into the genome of the bacteriophage, and then we found one of the promising protein encoded from this gene. Okay, this protein is technically an enzyme which is called lytic transglycosylase enzyme. This protein is produced from the bacteriophage in cytoplasm of the bacterial cell throughout the infection. But then during late infection, this enzyme will gain an access across the inner membrane here to the periplasm of the cell where the cell wall is. And the enzyme can degrade this cell wall, leading to the loss of integrity of the bacterial cell, subsequently leading to the cell burst, so that all the progeny of the phage inside the cell here can be released into the environment. Okay? So then, in order to tell whether or not this protein, LT enzyme, serve a role during the phage infection that triggered the morphological change toward the rounded structure, we perform a single cell morphological assay here. So the technique is kind of easy. We just clone the gene into a backbone, put this whole thing back into the bacteria, and then we produce the protein, only that particular protein, inside the cell, and see how this protein changed the morphology of the bacterial cell. Okay, so then comparing to this control cell again, they are in the rod shape in the red color here. They are happily dividing. Some of the cells started to divide from 1 to 2. Also, the DNA inside it is distributed all over the place, which is a feature of prokaryotes. Okay, but then during the expression of our protein, in the presence of protein, This protein alone can trigger the morphological change of the cell, including all of those human pathogens, including E. coli here, Vibrio, Pseudomonas, and also Salmonella here, toward the rounded structure. This protein also kill the bacteria and therefore showing the promising kind of potential activity of this protein in order to be used as the antimicrobial in the future. All right, so lastly, I would like to thank for sure our team of the team, including the PhD student who ran the project, and also of the team here, including Professor Puchit, who is the PCP inventor who developed the platform. And also thanks for sure all the funding resources, including Asahi Glass Foundation as well. Thanks to all collaborations on our phage work. And that's it. All right, thank you for your attention.
So I think the speaker welcome question.
Hi, thank you for presentation. I detected at least 2 different or 3 different database. First is your BCP database that is for response of bacteria to some selected chemicals, whatever you want in your database. That's BCP. Second is, I think it just started the MOK.
Right.
For phage.
Right.
It's a response of bacteria to phage you introduce.
Right.
Then third one I don't think you have, but I want to ask, do you have a database of
genome?
This phage?
Right.
Like, I understand phage, you get them from nature or?
Right, correct. So basically, phage reside in nature. We can just go out collecting all the environmental sample, bring it back to the lab and enrich the phage from the samples. So if they are present in the sample, they can be enriched.
Oh, so such a effort is ongoing in your lab?
Right. So in parallel to this project, we have been creating a library of the phage, because for the phage itself, it can be used therapeutically.
That's right.
They can be injected to patients. For those who are infected by superbug, they can be used as a drug.
Agree.
Right.
I see.
So actually, we have a lot more phage in the lab that can trigger the morphological change.
I see.
Right.
I see. So in Thailand, is it only in Chulalongkorn University you have only you have a phage database, or?
I would say that different group would have different phage, right? It depends on what they get during their experiment to enrich it.
I see. Thank you for your explanation. Thank you.
Thank you.
Other question? If not, I will take a chance. I see that your work may have maybe at least 2 implications for application. Like the first one, you show us quite a bit that you can use this morphology to kind of identify drugs or antimicrobial drugs or phage. But how would this be different or better than the common standard method nowadays? Would it be more rapid?
Yeah, right. It
How-
is
how
more
faster?
rapid.
How-
So
how
actually, we can tell the mechanism by a night. So actually, I would say that within 1 day, we'll be able to tell what the mechanism of the unknown compound.
Which normally how long does it take for normal method that they have?
The
like
problem of
tested?
the normal method is that what if you get the antimicrobial molecules into the lab? You would do some kind of the MIC,
Yeah.
right? And then another day later, you would know that, okay, this sample contain some antimicrobial molecules that kill the cell. That's it. This is what you know, right? But then for our BCP, we will know it within a couple hours. And in that particular hour, apart from knowing that it killed the cell, we can also tell the mechanism by comparing it to
that's
the.
what I think that you try to imply that, but I haven't seen you show example of different kind of mechanisms that can be seen from these
Actually,
results.
I need to skim it real quick, actually, because we don't have much time. But then here is the BCP. So actually, if you look into this, we have different cluster of the mechanism of action. Different drugs target different components inside the cell. For example, if we talk about Cipro, the drug that inhibits DNA replication, it will lead to the elongated cell while the DNA is stuck in the middle. For example, RNA transcription inhibitor like rifampicin, the morphology of the cell will be this. Instead of the DNA inside the cell will disperse throughout the cell. But then if we treat the cell with, let's say, protein translation inhibitor, the morphology of the cell will lead to this. The DNA will condense, making some kind of donut-like structure. Yeah, so then based on all of this morphology, it seems like the morphology here is kind of conserved. Because when we look into different pathogens, these from E. coli, but then for Ebommanii, the top critical listed pathogen in Thailand, they have the same thing, including other as well like Vibrio, Bacillus, and Staphylococcus.
So they respond the same way.
Right,
the morphology respond in the same way.
Most likely, yes.
Okay, and a little bit deeper, do you have hypothesis on the physical or chemical change that lead to elongation or round shape of the cell wall, or even the forming donut shape of the DNA?
Okay, let me get this delivered easily. I need to explain two things here, like a basic mechanism in cell. For example, RNA transcription, everything get recruited toward the middle of the cell. This is a process of RNA transcription. Okay, while in bacteria, this process is coupled with protein translation that everything got pulled apart to the cell membrane. Okay, so then once we inhibit one of them, it will lead to the morphology, the apparent morphology. For example, the protein translation try to pull everything apart to the cell membrane, right? If we shut it down, everything will be pulled toward.
Protein. I mean, when
in bacteria, protein translation need to be coupled with a cell membrane in order to synthesize protein.
Yeah, but when the cell sick and you said it get round shape, there will be more protein or less protein or different kind of protein. That's what I'm trying to ask.
What you're asking is the amount of the protein.
Either amount or type. Is it the change of the type of protein near the cell wall, or is it the change of the amount of protein?
I think it would alter the proteome of the cell. For example, a drug inhibiting ribosome, it will alter the whole pattern of protein expression, for example.
So it change.
Right, whole change of the proteome, like whole protein expression pattern.
Yeah. Would it be able to characterize these hypotheses or prove these hypotheses?
We would do some kind of the proteomics in order to see like the expression pattern of the protein.
Okay, thank you. For our last presenter? If not, then let's join me to thank Dr. Wallapon. Okay, I'm not sure if there is any activity after this session, but to close this session, I would like to thank all delegates from Asahi Glass Foundation, as well as all presenters, and I think representatives from faculties or Chulalongkorn University to be here and until the end. Okay, Thanks all. Thank you. Okay.